So, ladies and gentlemen, welcome to lecture Automotive Engineering 1. And I was starting to talk about the anti-blocking system for brake systems, which gives a much better performance than compared to the case that the driver itself is operating the brake pedal. So the advantage is that every wheel can be addressed, especially the front wheels and the rear wheels with different engagement of the wheel brakes, and this is adapted to the actual needs. And as you may remember, the actual needs depend on the friction coefficient between the tire and the road, and the friction coefficient depends on many parameters. So it was the temperature, it was the type of the road, the condition of the road, the weather conditions, and a lot of parameters from the tire. So what rubber compound is used and what tread pattern and things like that. And so also a lot of influencing parameters cannot be controlled by the driver, as he does not know exactly what road he is actually driving on. Temperature of the tires in the contact page is also not known from the driver. So it's nearly impossible to predict exactly what would be the appropriate brake pressure in the brake line in the front and in the rear, front and rear axle of a vehicle. So it is nice to have a adaptive technology, which always finds the appropriate level of braking pressure in the pressure lines of a braking system. Also, during braking, the speed of the vehicle is reduced. So, and as you remember, also the speed of the vehicle influences the friction coefficient. So, too many parameters to control in a predictive approach, and so it is used a system which is taking care on the slip of the tire and the slip variation of the tire. So the slip itself is not such easy to measure. There are wheel speed sensors. So every wheel is equipped with a wheel speed sensor. So the wheel speed is known very precisely, but it is a little bit more difficult to have a precise knowledge about the actual speed of the vehicle. Because under a lot of conditions, all these tires are operated with slip. So that means that the wheel speed is not identical with the vehicle speed, if we take into account the dynamic rolling radius. But there could be always a slip in between, and so this gives some uncertainty. And one opportunity to handle this is not to allow slip all the time on all tires, but to reduce also traction force or braking force for a short while in order to let the wheels rotate free, so they will not have any slip, and then a measurement of the wheel speed can be done. And so that's we need some alternating engagement of the brake, and in between we can make measurements of the speed of the vehicle. And if we know the speed of the vehicle, we can compare with the actual spinning speed of the wheels, and so we know also the slip. And this slip is an important quantity to decide if we have the potential to apply a higher brake pressure in the brake line, to request more braking force to be supported between tire and road, or if you have to release a brake in order to avoid too high slip. And on that chart here, we can see this is the characteristics of a tire, the red one, if a brake force is applied. So this is a free turning wheel without any slip, and then if the slip is increased, a braking torque can be transmitted to the road. And as explained several times, there is a maximum, and then above the maximum, the transmittable force is reduced. And so we should not exceed that maximum. So we should always stay below that. because here the brake force is easily to be controlled by the brake pressure given to the brake line. But if we exceed that maximum and we come into this region, here it's a pretty challenging thing to control the wheel, because here the braking torque created by the brake is supported by the inertia of the wheel, and this is pretty small. So goes very fast that the wheel comes to blocking, and this reduces the transferable force in longitudinal direction, and it further reduces dramatically the side force, which is the blue line. So you can see if we allow a high slip in circumferential direction at the wheel, so we reduce dramatically the side force, which is transmittable. So we may lose control over the vehicle if we apply a too high wheel slip. So we should always stay here in this area. So we have always some potential left, also maybe some high potential left for side slip. So this curve here means we are going straight forward, and this curve means we have a certain slip angle, and this gives 100% side force if we do not have any circumferential slip, but if we then increase circumferential slip, it goes down to 0. So the side force depends extremely from the circumferential slip of the tire. So that's the task of the ABS system, to keep the wheel operating here in that area on the left side of this maximum. And now this depends on the condition of the road. And we can see here this is for dry road. It's a green curve, so we can reach pretty high values of the mu adhesion. And a wet asphalt, it is reduced. And it's dramatically reduced if there's snow on the road and also blank ice. And with blank ice, it does not matter where we are with the slip. It's everywhere pretty worse. With the snow, there would be a better result if we go to pretty high slip, because then we will do something like bulldozing. So there is a little hill of snow is created, which is in front of the tire, and will be just pushed by the tire forward. And this needs some extra force. So if we allow to block the wheel on snow, we will have a little bit higher potential to support forces from the tire to the road. But anyhow, it is anyway it's operated here because we want not to have a very large slab here. Then maybe we come back from snow to a asphalt road, and then we need to change completely with the slip. So this and this needs to be pretty fast. So it's better to stay with a slip in a moderate area, so that we have under all conditions the chance to transfer a high amount of force between road and vehicle. And so this is a control range. The yellow area is the control range of the ABS system. So always stays with moderate wheel speed. And this is a simplified drawing of the system, of the ABS system, with the most important components. So first, it's important to know the wheel speed. Otherwise, it's not possible to control the system. And these are the wheel speed sensors, which are called here, indicated with the number 1. So this is at every wheel there is a ring with a lot of slips, nuts and grooves around the circumference is put on the wheel, and there is a inductive sensor close to the top of this ring. So the ring looks a little bit like a toothed gear, and so if a tooth is close to the sensor, this gives a different magnetic flow. And if there is a groove directly where the sensor is located, then we have again a different magnetic flow. And so we can distinguish. So this creates a sequence of pulses, and from the frequency of these pulses, we are able to calculate the wheel speed. And so this can be done for every wheel. Then, of course, we need the traditional braking system consisting out of a pedal and a main brake cylinder where a high brake pressure is created by the driver. So it is pressing the brake pedal. What is not shown here on this slide is the booster, so-called booster. This is an amplifier for the pressure created by the person. So this means that it's a little bit more comfortable for the person. Need not to press such hard the brake pedal to create a high brake pressure in the main brake cylinder. So we have here a high pressure available. So this is a fluid used to transmit this pressure through the pressure lines, which are thin hoses going from the main brake cylinder across the vehicle to the wheels. And only the last few centimeters a hose is used, a flexible hose, which allows the wheel to be deflected during driving and to be steered and so on. And so through that channel, the brake pressure is transmitted from the main brake cylinder to the wheel brake cylinder. And the wheel brake cylinder operates the brake pads. It presses the brake pads on the brake disc, creates a vertical force on the brake disc, and this creates a sliding friction, and so the force, a brake force or a brake torque is created, and in the tire this is transferred into a brake force which acts on the road. And these wheel brake cylinders need to be controlled, and that's done by the so-called hydraulic control unit, which is here also directly close to the main brake cylinder. So this is a control unit, a hydraulic control unit. It's made out of a block of metal. No, typically it's aluminium, and there are a lot of holes are drilled in, and in this hole a lot of valves are integrated, and so these valves are controlled electrically by a electric control unit. So this is a so-called ECU, and this is the HCU. There's a hydraulic control unit, and this is a electronic control unit. And this electronic control unit gives controls the valves, opens or closes the valves upon demand, and controls the speed, the slip of the wheels. And there's also a control light number 5, which indicates that the ABS system is operating. So this is information for the driver. Tells the driver, oh, obviously you are in a critical situation. Braking system tries hard to realize best braking, and so please pay attention. So that's the reason that the driver has a control light, which gives them some feedback. Okay, so these are the main components. And these control valves, which control the wheel brake cylinders. Here's the wheel brake cylinder. This is the brake disc. Here are the brake pads, and this part here is the brake cylinder, wheel brake cylinder, which presses the brake pads onto the disc. And this is a brake line here, this one. So this comes here from the main brake cylinder, providing the braking pressure. PB means braking pressure, and so the fluid transmits this pressure here. So there is not much flow in the fluid. There's only a few cubic centimeters of flow during a braking operation. This is mainly a transport of pressure on the fluid. And now, if in a standard operation or in a moderate braking, if there is no emergency case, then the driver just presses the brake pedal. This creates the brake pressure in the main brake cylinder, and this is transferred here by this line here through that valve, which is on a standard base. It's open, as you can see indicated by this double arrow. It's open, and then the pressure goes here to the brake cylinder, and the brake is activated. And if the driver is releasing the brake pedal, then this pressure is reduced, and consequently also this pressure is reduced, and then the brake is released again. So that is how it is operated normally. And only in extreme cases, if there's really an emergency and the driver requests a pretty high deceleration of the vehicle, then he presses the brake pedal pretty hard, and this may cause the case that the brake got a too high brake pressure, and the wheel is blocked. And then we have a problem with stability with the car, and with the problem that the overall force transmittable is reduced. And so we would like to avoid that. This is a situation where now this system comes into the game. So if the system recognizes that the brake is not operated in the optimal way, then it is able to close that valve here, in order to avoid that the brake pressure, the increasing brake pressure created by the driver, is transmitted to the wheel brake. So you can just close that, and so that the brake, even if the brake pedal is pressed harder, this will not increase the brake pressure at the wheel anymore. And if it was already too high, the pressure was too high, then it's possible, if this is closed, then the second valve, which is normally closed, can be opened. So there is a current used. If the current is flowing here in the valve, it opens, and then the pressure can be released. So this line here goes to the reservoir, a small reservoir where the fluid can go in, so this will reduce the pressure. So these are the both valves which can be controlled by the ABS system. And you see, this is a spring here. This spring makes sure if there is no current applied to the valve, it is open. So also if the system is not correct, maybe there is a failure or an error, if no current is available, because of what reason ever, so it will stay open, and this will always stay closed. So at the end of the day, the driver is able to brake by himself. But if the driver is not doing a good job, so then the system can close that and can open that if necessary, and can control an appropriate pressure here on the wheel brake, which avoids a slip which is too high. You can see here is also a reverse valve. This reverse valve allows also a flow of fluid from in this direction. In the case that this is closed, it allows a flow of fluid here in this direction. Can you imagine what is the reason to implement here this reverse valve? Well, why could it be necessary? Yes. Exactly. So if during a emergency braking system, the ABS system is active, it has closed this valve, and it is controlling the brake pressure here. And then the driver decides, oh, I want to stop braking, because maybe a situation has changed. Yeah? Maybe there was an obstacle in front of the driver, maybe another car, and then the car, maybe it just vanished because it changed the lane or whatever. Yeah. So and then there is no problem anymore. So also because of safety reason, the driver would like to stop this emergency braking, so he will release brake pedal. And release of brake pedal always needs to reduce the brake pressure on the wheel brake. Yeah? And if this is closed here, and here the pressure would be released, nothing would happen. So the high pressure would still be here, and we will still continue emergency braking. So in order to avoid that, in order to make sure that always the driver can overrule the system, this reverse valve is necessary. And if he reduces here the brake pressure in the main brake cylinder, then we have here low pressure, here's a high one, and so we will have a flow of the fluid here over this reverse valve, and also the pressure will be reduced here in the brake pressure, in the wheel brake. this is a full system for a car. So we have all the parts here. This is a brake pedal. Here is also the booster. This is this braking pressure gain. And this is a main brake cylinder behind. And here is a reservoir on top. Here's just environmental pressure inside, and it's just a reservoir for more braking fluid. And so if the brake pedal is pressed, the booster amplifies the brake pressure, so we will have a high pressure here in the main brake cylinder. And if more brake fluid is necessary, no problem. Here's enough in the reservoir. So then the fluid will be pressed here along the line, and you can see there are two lines, one to the left, one to the right. So this is a circuit 1, and this is circuit 2. This creates some redundancy, helping if one circuit will be out of order, then we have still a second one, yeah, and we can still brake with a reduced performance, of course, because only two wheels will be braked. And so this first circuit is typically for the rear left, and this is the front right. Sorry, it's not translated. This is from German, hinten links, vorne rechts. So this is the left, rear left, and the front right. So it's diagonal on the car, and you may understand why it is diagonal. It is because if for example the left side and the right side, this would be one circuit on the left and one on the right, so this would create a yaw torque around the vertical axis of the vehicle. So this will indicate a steering effect, and in order to avoid that, and also if it would be front and rear, two different systems, maybe if the front braking system will be out of order, then we will have only brakes on the rear, and it's pretty dangerous to make emergency braking only with the rear axle, because the car will become immediately unstable. And so in order to avoid that, we have two circuits, and there's always at least one wheel at the front, and it's diagonal in order to avoid a yaw torque around the vertical axis. So that means let's have a look to brake circuit 1. So the brake pressure goes in here, it goes here. And so this valve is typically open. So this is the inlet valve, and through that inlet valve, the brake pressure goes here to the brake, to the wheel brake. And this is the outlet valve. So if necessary, this can close, this can open. And after the braking, the brake fluid, which was flowing here from the main brake cylinder here in this direction and then going back here, is stored in that reservoir here. So there's just some air in, so this can be compressed, and so the brake fluid can go in here. And after the braking, if the braking maneuver is finished, then here this pump and also the brake is released, so we will not have any high pressure here in the main brake cylinder, so just an environmental pressure here. So then this pump will bring the fluid from this reservoir back to the main reservoir here. Yeah? So and here it is just the same on the right side. So this is how it works. And of course also this at the same time, this is also supplied here with if the inlet, as long as the inlet valve is open, also the brake fluid goes here. So you see everything is double. So there are two pumps. There are in total 8 valves, so 4 inlet and 4 outlet valves. But there is only one motor. This is because of cost reason and because of space needed and so on. There's only one motor. So if the motor fails, okay, it will not work anymore. So then it could work as long as enough brake fluid is here in the reservoir. Yeah? Then it could still work. Okay, but what is always possible is that the brake will be used in a standard way. So the most severe thing which could happen is that the ABS function is not working. Now let's have a look at what happens during the operation. So This one? You are talking about a normal braking or a ABS braking? ABS braking. Hmm. Yes. This this is not a one-way valve. No. This one? This one is a one-way. Yes. Fluid can only go from the brake, from the wheel brake back to the reservoir. This one is closed. Hmm. Yes. If the brake pedal is released during operation of the ABS system, let's assume that the ABS system has closed this valve here. This would mean that there is no connection anymore between the main brake cylinder and the wheel brake. Yeah, so we have a high brake pressure here, and if the driver decides to stop braking, then he can release the brake pedal, and then this pressure here will be reduced, and the brake pressure, which is high here and low here, can go over this valve here, so the fluid can flow this way, so it goes back, and also the brake pressure will be reduced in the wheel brake. That's the function, yeah. And if this would be not here, this would be not possible. As long as this is closed, there will be no contact between the brake pedal and the wheel brake. Yeah? But the driver needs always to have the control. If the driver decides braking activity should be stopped, then it should be stopped immediately. And so he leaves the brake pedal, and so we will have here no pressure anymore, but here is still a high pressure, and so we will have a release of the pressure over these valves. Yeah? Okay. No, this is it's a mechanical valve, but it is controlled electronically. So there is a magnet inside, and if there is a current, then this magnet will shift the mechanical valve, so it will open or it will close. And in this case, it is always open if there is no current, because of this spring. The spring makes sure that it's always in the open position. But the current will overrule the spring, so it will shift the valve here to the left, so then it's closed. Yeah? But if the current stops, then the spring will automatically open the valve again. So this is, yeah, if a failure takes place, the valve makes sure that this valve is open. Yeah? Okay, so then this slide shows what happens during a ABS activation. And I have explained that the ABS is using the slip to control, but it is not only it's not only making a measurement of the slip, because as already told, it is not easy in every second to, so it's nearly impossible to have a continuous information about the vehicle speed. We can have a continuous information about the of the wheel speeds of all four wheels, but not of the speed of the vehicle. And so this is the reason that also another quantity is used for control, and this is the variation of the slip. The variation of the slip goes very fast if you are close to the maximum of this mu slip curve. Yeah? Especially if we exceed the maximum of these tire characteristics. Then there will be a very, very fast change of the wheel speed, because the wheel is going to block, and this goes pretty fast. So this strong acceleration of the wheel speed, so which is the slip gradient, so this can be also recognized by the wheel speed sensors. So the wheel speed sensor is sensating the speed of the tire, of the wheel, but also the speed variation. And so let's assume that the vehicle is driving with a certain speed v. We do not brake, so the speed stays constant. And this means also we do not have any braking pressure. Here, this P means braking pressure. Then at a certain point in time here, we start a partial braking. So this means we only press the brake pedal a little bit. We have created by that only a small brake pressure. And so we will have some reduction of the velocity. So if we apply a constant brake pressure, this will create a constant normal force of the brake pads on the brake disc, and this will create a constant brake torque, and a constant brake torque creates a constant brake force, and the constant brake force reduces the speed linear over time. That's what we can see here. But now maybe here an emergency situation is coming up, and we need to brake harder. So that's what the driver is doing. He is pressing the pedal harder, so the brake pressure increases. And then here we are coming to that point where we have this vertical line here. So starting from that, we are coming here to a point where the gradient of the wheel speed is increasing, and there is a threshold. So if the wheel acceleration exceeds a certain threshold, which is set in the system and controlled by the electronic control unit, then the valve number 1, the inlet valve, is closed. So that's what we can see here. So B means, no, sorry, this was, okay, first only the inlet valve is open. So this is A. And then this emergency braking starts, and we come to the point that we have we exceed the gradient, we exceed this the threshold value of the wheel acceleration. So then the system tries to avoid that the brake pressure in the wheel brake is exceeding. So it stops this increasing by closing the inlet valve. That's case B here. Both valves are closed, so the inlet and the outlet valve is closed. That's here for a short while. And so it was initiated by the threshold of the wheel acceleration, and then, but it's still continuing to reduce the speed. So as you can see here, this is the wheel speed, and that's the vehicle speed. So the vehicle reduces faster than before, but slower than. So the gradient is much smaller than the gradient of the wheel, because the wheel has only a small inertia. So it gets, it tends to block. And then a second threshold is reached, and this is now a threshold of the slip. So that means with a certain slip detected by a comparison of the wheel speed and the vehicle speed, and the vehicle speed is always an estimated quantity, then a second action takes place. Now we come here to this mode C, which means only output valve is open. So that means now input valve is closed, and the further increase of the brake pressure in the main brake cylinder, which is created by the driver, is not transferred to the wheel. And now at the wheel, the pressure is even released and reduced by opening of the outlet valve. Yeah? So this reduces immediately the pressure in the wheel brake. So that's the wheel brake pressure, that's the main cylinder, brake cylinder pressure. This stays on a high level because the driver is braking like hell. He wants to stop the car. Yeah? And so now this opening the outlet valve will reduce the brake pressure to a limit which is more acceptable. So this, okay, so it goes to that point here. So this outlet valve is closed again if the wheel acceleration is now coming again to this threshold, but now from above. So the wheel acceleration is reduced. There's still acceleration, but it's reduced, and it passes again this threshold, and then the outlet valve is closed, and then the pressure is kept constant for a while. So that means here again we are in the mode 2, which means both valves are closed. Now we are here. And now the pressure is on on a level in the wheel. The wheel brake pressure is on a level that allows the wheel not to further reduce its speed, but to increase the speed. So now the vehicle, the inertia of the vehicle is still pushing forward the wheel and accelerates the wheel again. Pressure is low enough that wheel can accelerate again. So it stays closed for a while until to that point. And then the slip is measured again, and we see that now the slip is pretty small. So the wheel has almost the same speed as the vehicle. So that means we are not making good use of the braking force potential, which could be provided by the wheel. So we need to increase the slip again. And so here with some short boosts, the inlet valve is opened, and by every short opening, the brake pressure in the wheel brake is increased, which will increase the slip, will increase the force, which can be transmitted to the road. But then we come again into that situation, which we have here also, and now everything starts from the beginning. And such a cycle here will, until that point. So such a cycle will last for around about 200 to 250 milliseconds. So that means we will have 4 to 5 of those cycles per second. And that's what you also can hear if you activate ABS systems. I don't know if you have ever tried it in your car. Well, you can try it if nobody is behind you, and make just a emergency brake situation, press brake pedal pretty hard, and then the ABS system will start. You can hear that. Yeah, so there's a sequence of opening and closing of the valves. You can hear there's a sequence like that. So this is an indicator also for the driver that the ABS system is active, which is normally not the case. So maybe this situation, you are facing that situation once a year or whatever. So it depends on your driving style, but normally not. Yeah? So that means it's a pretty fast control, and it makes sure that the wheel slip is always around an optimal value. It goes hard to the maximum, maybe a little bit above the maximum, and then it just immediately capped, and the outlet valve is open so that it will not go too fast. And so we are pretty close to the maximum, which is possible. We are not completely all the time at the maximum. It's always a control cycle which goes around, but it is much better than every driver can do by himself. So this is a system which is very, very helpful to make best use of the braking performance of the tire road contact, by always staying very close to the mu at value, and it keeps also the vehicle stable, because if we not exceed the maximum, we have always side force left, and we can make sure that we can steer, and the vehicle will not get unstable and will not start to skid. Yeah? So that's what we can do. Yeah, the ABS system may also be used for more sophisticated application, but then it needs also to have a extension, because the activity of this system is limited to the case that the driver is really creating a brake pressure. If the driver is sleeping, this system cannot help. No? And so this leads us to the next type of system, which is the ESP system. Okay, maybe I should make one remark. I forgot one thing. If all four wheels are controlled from the ABS system in a way that it makes best use of the friction coefficient which is available between road and tire, it may happen that, especially in winter time, that we are facing a situation where maybe on the right-hand side, so close to the at the borderline of the road, there might be maybe some ice, maybe some frozen water, and in the center of the road maybe we have asphalt. So this means that on if it's a right-hand driving situation, this means that on the right side of the car we have very low friction coefficient, and on the left side we have a much higher one. So if we fully apply the brake, this will cause on the left side strong brake force acting on the vehicle against the driving direction. On the right side, we are on the ice, only a very small braking force is transmitted to the vehicle. This will create a strong torque around the vertical axis, and the vehicle will start to spin around that vertical axis. So this is a steering response, but the driver is not steering, the driver is braking, wants to reduce speed of the vehicle, and now the vehicle starts to turn around. So this may be pretty critical. And to avoid that, a strategy is used, for example, to wait a little bit with the increase of the brake pressure on the high mu side, in order to give the driver a little bit the chance to recognize what happens. So this will reduce the maximum force which is transmitted, yes, but it avoids that the car starts to rotate around the vertical axis. And so the driver can feel, I'm braking, and now I have a tendency of the vehicle, a steering tendency, and I can use my steering wheel to work against that. So that's a way it could be handled. Another way is that if there is a electric steering system available, which is the case in a lot of cars today, so then this electric steering system can be used to immediately control the steering and to keep the car straight forward. Yeah? So if the braking causes steering to the left, so the steering system will overlay a steering angle which will compensate that, so that the vehicle is still driving forward. And that's how in modern cars it is done. But electric steering system is necessary for that. Okay, now the next a little bit more sophisticated case is if there is not just a straightforward driving requested, but the driver intends maybe to drive certain maneuvers with a steering system. Has to follow a steep curve with a small curve radius, and so he needs a lot of steering. And under this condition, it could happen that also the centrifugal forces on the car will act in a way that the vehicle starts maybe to skid, or even it could start to roll over. And so I would like to come up with some small, with a simple drawing. So let's assume we are looking on a vehicle from behind. And this should be the cross-section of the vehicle seen from behind. So the car is driving in front of us. And so I make it pretty simple, so there are no wheels visible. This is the ground, and the box on top is the car seen from behind. So there might be here a center of gravity somewhere here. And the car is going into a left-hand curve. So this will mean that an inertial force is pulling to the right with a force which is mass of the vehicle, inertia, times the lateral acceleration. So this is a centrifugal force. The Fy is a centrifugal force. And so we know centrifugal force is mass, which is rotating the radius of the curve times omega squared. Omega is the angular speed while driving in this curve. We also know that omega is the speed on the track divided by the radius of the curve. We can make use of that and put it in here. So then we got the expression that this is m times r curve times velocity of the vehicle squared divided by curve radius squared, and this is m times v squared over r curve. So we can also use this expression here. So this is one force which is acting on the vehicle. And there's another one which acts in the opposite direction, has the same magnitude but opposite direction. And this is, of course, we have also here a gravity force, which is m times acceleration of gravity. And this causes a friction force which is mu at maximum. It's mu at. If we don't exceed the maximum, we can use mu at. So these are the both forces. And of course, the limit is given, the curve limit, or the highest speed to go through the curve, or the smallest radius is given when the both forces are equal. So this means the m times g times mu at under this condition is the mass times ay max. And I add here also a skid, because now we are talking about skidding. So this is it's a skidding limit. So the vehicle will start to skid if the centrifugal forces exceeds the friction force which can be supported by the tire wheel road contact. And this is equal to mass times vehicle maximum vehicle speed squared divided by the radius of the curve. And so now we have three expressions, and if we compare the both first one, the first both, so from that we can you see we can cancel the mass. It's available in both, so we can find from those both we can find a expression for the maximum lateral acceleration concerning skid. And this is just mu at times g. And from the first one and the last one, we can get an expression for the maximum velocity of the vehicle. We call it here limit. And this is also skid. And this is okay. We need the square root right now. This is the curve radius times mu at times g. Again, the mass is cancelling out. So we have found two relations which are valid at the skidding limit. No? So this is one thing which could happen, skidding. But another thing which could happen is rollover. So there's also a limit, roll over limit. And Again, we are looking in driving direction. We see the vehicle from behind, and we have got now here this is a vehicle. Now I also use here the tires. I indicate the tires in my drawing, like that. And here's the ground again. So tires are on the ground, and this is the road. Again, we are going in a left-hand curve. So this is a center of gravity again, and again we have our centrifugal force, which is exactly the same as before. So this is m times a lateral, a y, then, or this we can express it as vehicle speed squared by radius of the curve. So that's exactly the same. And so this force, this lateral force, is acting on a certain height above the ground, and this is h. Yeah, it's the height of the center of gravity above the Earth is h. So this gives a control arm or a lever arm, and so we have a force on a lever arm. So this is a torque, and there is of course another torque. So if this is pulling on here on this graph to the right, because I'm going to a left curve, this here is a critical rod contact. So this will be the pivoting point for rollover. So if this centrifugal force here above is too high, then the left wheel will lift off, and the vehicle will rotate around this contact point of the right-hand wheel on the road. And there is another torque which is working against that rollover, and let's assume that the distance between the both wheels, left to right, is s, or no, it is called here st. So, and which means that if the center of gravity is in the middle of the car, which we could assume, then we will have here st divided by 2. And again, here is a gravity force acting on the center of gravity, and related to that pivoting point here on the right tire, this gives a torque which is st divided by 2 multiplied with the weight of the vehicle. And we are reaching the maximum if those both torques are equal. So we can write m times g times st half. This is the torque which tries to avoid rollover, is equal to m times a y max roll times h. And of course we can also use the other expression for a y. This is v squared by r curve times h. Again, we have 3 expressions and we can compare, and so we use 2 by 2. So we get, if we use the left one and the middle, we got again a expression for the maximum lateral acceleration at the rollover limit. This is st divided by 2h times g, and there is also a vehicle limit speed for rollover, which is again square root out of curve radius times st divided by 2h times g. So we have now 2 expressions, 2 sets of expressions, one for skidding limit, one for rollover limit, and we can now ask the question, what is worse, to skid or to roll over? And I think the answer is easy. We should avoid rollover in any case. And if we need to make our choice between those both catastrophes, we will take the skidding. Yeah? So this means the car should start skidding first, which means that the maximum lateral acceleration of the vehicle for skidding should be lower than the maximum lateral acceleration for rollover. No? Which means, with other words, we are using this, and we're using that equation from that. So if skidding should be first, skidding should be first. And from that, as a consequence, we get that the mu at times g must be smaller than the st divided by 2h times g. And from that, we get that the mu at should be smaller than st divided by 2h. Or we can say it also another way around. We can say the st should be always larger than 2 times mu at times h. Because skidding is less critical than rollover. Rollover means that the car is leaving the wheels. And if during a rollover, the car will be damaged completely. During a skidding, the vehicle is always standing on the wheels, and if the road is wide enough, if there is no other traffic, it may have no consequences. No? That's the reason. And if we want to prefer skidding, then it is necessary that the skidding limit is lower than the rollover limit. No? The car should not start to roll over before it starts to skid. So the borderline for skidding must be lower. Yeah? So we can write these also different. We can say mu at times 2h should be smaller than st. Maybe seen from somebody who is going to do a construction and a design of a vehicle, it's important that the wheelbase is large enough and the center of gravity is not high above the ground. No? Because the left side should be small and the right side should be large. And this is, for example, done with race cars. They are very wide and they have a very low center of gravity. And this allows the racing cars to avoid rollover, even in a situation that the mu at on racing tracks is pretty high. So this limits also the maximum curve speed of heavy trucks, for example, if this is a truck which has a high load, and this creates a very high center of gravity, maybe 1.5 to 2 meters above ground. So this limits the maximum curve speed to maybe 2 or 3 meters per square second, otherwise it will roll over. So this should be avoided in any case. A passenger car can go much faster, or with more lateral acceleration. So passenger car typically can exceed lateral acceleration up to 1g, and the race car is up to 3g. No? Okay, but this is something we need to take into account during the design phase of a vehicle. And all vehicles which can be found on the market have this design inherently applied. But anyhow, it could happen that a dramatical situation takes place and the vehicle will start to get unstable, so that a skidding takes place because of strong steering input, for example. And this could also turn into a rollover. And I need to explain one phenomenon or two phenomena which are important in this relation. And this is that the vehicle can start to oscillate. So there could oscillations can take place. And these are two different oscillations which are important in this relation. One is oscillation around the yaw axis, so the vertical axis of the vehicle. So if I steer the vehicle, and then I steer back, and maybe I steer again, and I steer back again. If I do it like that, it could happen that the vehicle starts to oscillate around this vertical axis. So it's a gear oscillation, a yaw oscillation. This could happen. It's a yaw oscillation. Another oscillation which could happen is also during steering. This is a roll oscillation. Because if I go into a curve, always the vehicle will tend to roll to the outer side of the curve. Yeah? If I go in a curve like that, the vehicle will tend to roll in that direction. No? And if I do a steering, alternating steering action, so I go into one direction and then I go into the opposite direction, so then the car will go first, will roll first like that, and then it will roll like that. And also in this around the roll axis, oscillation is possible. And maybe I can make it plausible by if you think on a simple oscillating system like having a mass carried by a spring. Yeah? So we have two essential elements of a system which creates the ability of the system to oscillate. If I introduce a little displacement of the mass and I keep the top of the spring constant on the same height, and then I release the mass, then you know what happens. The mass is pulled upwards by the spring, and because of the inertia, the spring is not stopping in the center, but it goes further. And then the spring is compressed. Then now the spring creates a force backwards, downwards. No? This will stop somewhere the mass. So, and then the mass will be accelerated in the opposite direction. Now it gets a speed, has got some kinetic energy, is crossing the center, but because of the kinetic energy, it just continues. And then the spring will be elongated and creates a force upwards. So we have a system which is able to oscillate, and this goes on and on and on, and if there is no damping, it will never end. Yeah? So that's an oscillation. And the same could happen with a vehicle, because around the roll axis, we have a moment of inertia. Yeah? There's distributed mass in the vehicle. This creates a moment of inertia. And we have, of course, a spring, because on the left side, on the right side, the wheels are connected to the vehicle by body springs. So there's elasticity. So it's the same as this spring pendulum could happen with a vehicle. So if we steer and we let the vehicle roll to one side, and then we steer in the opposite direction, and it rolls back to the other side. If we do that excitation with the right frequency, we could meet that oscillation frequency of the vehicle. Again, back to the simple situation, I have a spring and a mass. You know, when I displace the mass and I release it, and then I let my hands off so that the pendulum can oscillate free. It will oscillate with a very specific frequency. Yeah? That frequency does not depend on my displacement, which I have introduced in the beginning. It's a system property. This frequency is a system property. It can be calculated from the spring rate and from the mass. Okay? The same is with the car. This roll oscillation is a system property. It can be calculated from the inertia and from the spring rates of the body springs. Yeah? And by the way, the sway bars. But okay, this is not so important to see it with all these details. The only thing is, it is able to oscillate, and it has got a own frequency. And now you know what happens if a system which is able to oscillate will be excited with the right frequency. Yeah? So if I not just keep it constant, but I will go up and down, and here's the spring and here's the mass, and if I exactly meet this frequency of that system, then it will end up with very, very high oscillations. This is a so-called resonance catastrophe. And this could happen with the car. So if I excite the car with an appropriate steering action, with the right frequency, and the frequency is about between 1 and 2 hertz. Yeah? 1 and 2 hertz. So that's a steering speed, steering frequency which a person is able to do. It's faster than normal steering, but it's not impossible. So I think everybody can do steering activities with up to 2 hertz. So it's possible to excite the vehicle exactly in its rolling frequency. And of course, also the same thing with the oscillation around the yaw axis. Also here we have an inertia, we have a elasticity, we have a lining torque created by the tires. Yeah, you know, if you go into a curve and you take off hands on the steering wheel will go back alone by itself. Yeah, goes back into the central position. That's a back driving torque created by the tire road contact. This takes place in the vehicle, and creates a force which is similar to that spring force. So we have also this oscillation, and this is also coming along with a certain frequency which is very, very similar to that frequency which is given for this roll oscillation. So roll oscillation and yaw oscillation have very similar frequency. This creates a system which is very easy to excite to very, very strong oscillations, so with large displacements, if the steering action is done with the right frequency. Yeah? Is this plausible? And if we go with a vehicle in a situation like that, this is a so-called double lane change. A car is coming here. Here are some pylons which indicate the left and the right border of the track where the car should go. And this has a certain width which is given here, so it depends on the width of the vehicle. So the vehicle is coming here with a certain speed, and then it should make a lane change to the left, and then it should make, after some meters, which is defined precisely, it goes back to the old lane where it was coming from. So this is called a double lane change. Something you do if there is an obstacle on the road. For example, like that situation here. There's an elk or moose on the road, and it's just stepping on the road. You're coming along, and you have to drive around it. And what you avoid is exactly that situation, that the car is doing a rollover. So that test here is driven under certain conditions. You see there's a certain engine speed required and so on. And we start with low speed. And then we go this curve. And if it is possible to follow this curve without hitting a pylon, it's fine. Then we do it again with a higher speed. And we stop if the first pylon was hit. Okay? So this is the final result of this test. Maybe we can go with a car 70 kilometers, maybe 80 kilometers. If it's a good car, maybe 90 kilometers, but somewhere around that, then it stops. Because what is happening if we go faster and faster and faster? We need to steer faster. No? And if you drive, try to imagine you drive a double lane change. So I'm driving here, and here is the other lane. So if I want to go to this lane, I have first to steer that. Then I go back. Now my car is driving diagonal. In order to come to the second line, I have to do something like that. So then I'm oriented in that direction, but now I'm here. And then I have to go that. Now I'm driving in this direction. And again, I have to steer that. So what I have to do is that and that and that and that. Okay? And if I do this fast enough, and the steering speed depends on the driving speed, of course, because I have these pylons. Huh? So by going faster and faster, I have to increase my steering action, and at a certain speed, I will meet with my steering action exactly that resonance frequency of the yaw oscillation and the roll oscillation. And if so, then I will have very, very severe wheel load variations. Yeah? Because I will have a very strong roll of the vehicle. And so then I go into into one curve. So I will have a very high force on the front outer wheel, a very high vertical load in the curve. And because I have a very high load on this specific wheel, a very high friction force can be transmitted. Yeah? And if I do this steering such fast that my roll angle, and because of this resonance, the roll angle gets so large that the full deflection range of the spring on this wheel, of the body spring of this wheel, will be needed. Then, at the end of this, if the spring is completely compressed, at the end there is a end stop. This is a rubber element. If the end stop gets in contact with the car body, the deflection of the wheel stops abruptly, which gives an extra force input in vertical direction. So we have like a force peak, and this creates a super high friction, which a super high braking or a side force which can be transmitted between the tire and the road, so that it is more or less that the wheel is welded to the ground in that situation. And this is the situation where now the rollover takes place, because it cannot slide anymore. It has so high vertical forces that we have super high friction forces transmittable, and then the vehicle will not slide anymore. It will roll over. Okay, and that's a situation. What is shown here, for example, if you go through that curve, you can see this is exactly the double lane chain curve test with the pylons. So the car has already hit a lot of pylons, and it is going here on the upper left. It's going here into a right-hand curve. You see, it has completely lifted off the inner side of the vehicle. It's only standing on the outer side, and this gives such a strong deflection of the wheel. Relatively, the wheel comes very close to the car body. So there is this end stop, and if it hits the end stop, this is an extra force giving in a vertical direction to the road. So we have a super high friction force which can be transmitted, and then the rollover takes place. And also what you can see here from the lower okay, normally there should be a magnification of this lower picture here. I think, I don't know if it is visible, but you can see that the vehicle is not driving the tire as it should be. Normally the contact should be here, but now the contact is here on the side of the tire, and there's a completely different rubber, and this rubber on the sidewall is more soft, and it creates a higher friction coefficient. So in this moment, not only the end stop creates this extra vertical load, but also the side wall of the tire creates a higher friction coefficient. And then this rollover starts. It is similar like the car will hit the curbstone and it avoids a further sliding. No? And this leads to that situation here in 1997, which was really a disaster for Daimler company in those days. Daimler was known worldwide to create high-quality cars on a very, very high safety level. And then in 1997, Daimler decided to bring into the market a very small car they have never done before. It was a very small car. It was an A-class, and this was a very visionary concept because this car has a double underbody. And in this double underbody, it was prepared that the battery for electric drive should be implemented later on. Now, this was 20 years ago. Now this model has vanished from the market before electric vehicle was realized. But anyhow, it was thought that it should be the first electric vehicle from Daimler. And because of this double underbody, the center of gravity was pretty high. So this car was more critical to be affected by rollover. And that's what was happening here. And Daimler was thinking, what can we do? And 2 years before, they have implemented the so-called Electronic Stability Program, ESP, in their first model, an upper class model in the S-Class. It was introduced in 1995. And so they had the technology in-house to avoid this rollover by this stability system. And so it was necessary, so they were forced to, in order to save their investment for this small car and to be able to bring that car into the market, it was necessary to bring in this ESP system, the stability system, into this small car. And that's something car manufacturers normally not do. A new technology is always introduced on the high level, on the high end, on the upper class vehicle, on the premium vehicle, which are very important, very expensive. And if a car which costs 200,000 euros or 100,000 euros, it is not critical to add some more 1,000 euros, maybe to increase the price by another 3,000, 5,000 euros is not a big deal if a car is such expensive. So new technology always is introduced into the market via the top class cars. But in this moment, it was necessary to do it vice versa, to start with the smallest car of all cars which were produced by this company. And so this was the start of ESP system, to introduce it super quick into the market, because if the smallest car, the cheapest car of the company is equipped with this superior safety feature, all other cars need also to be equipped, otherwise it is not accepted in the market anymore. So Daimler has to bring into the market this system, this ESP system, within all models. And as a consequence, if Daimler is doing so, BMW needs to do, Audi needs to do, everybody needs to do. So it was a super fast market introduction of a very, very good technology. And this allowed a situation which was pretty seldom in the development of technical objects, to compare the situation before and after introduction of ESP into the market. And before, there was a much higher level of traffic accidents, of injured people, and of killed people in traffic. And after introduction of the ESP system, this was reduced by around about 40%. So it was a big step forward in vehicle safety to introduce this system. And it was caused just by one journalist, which exactly did this test here and blamed Daimler. It was a catastrophe in that moment for the company, but it was a very, very good step forward for safety, for traffic safety. all over the world. I brought here a sequence of some pictures showing a situation which would benefit much from an ESP system, but the cars which can be seen here, they don't have ESP system. So it's a little bit small. I took some snapshots from a video some years ago. Unfortunately, the video is not available any longer. What we can see here is a traffic situation. Here's a street with 2 lanes in one direction, in every direction, and there is some grass here in between. And we can see here is a red car which intends to turn left, and here is another road, so he wants to go left. And here in the sun there is another car coming, and this car is coming here on seen from his side on the left lane, so on this lane here. And so this red car here is not stopping properly. You can see there's already the stopping lights are active, but the car is not stopping immediately. And this car here in the red circle is now running into problems, because the car in the orange circle is a little bit too far on the track. You can see now it is here on the track of this car coming from behind. So this car needs to erase, and it steers to the right. It was driving straight forward, and now it steers to the right in order not to hit this car here. Then you see now he is recognizing that something happens. Now he stops a little bit late. So now this guy here has a hard work to do, because he was first steering right. Now he needs to steer left again in order not to hit the curbstone here. And as you can see, he managed that situation. Right? It's very narrow, but he did it. And so he has first he was going to the right, and then he's going back to the left. So he has already done a double lane change in a very short time. So it was super fast. And he, of course, he is with his steering action very close to these oscillation frequencies of the vehicle. And but he passed the curbstone. You see, this guy is now stopping. And now he escaped the curbstone, but now he's approaching these grass here in the center, and that's also something which would be not a good idea to drive over that. He should stay on the road. So now he needs again to steer, now to the right, in order to come back to his old lane. And so he's also managing that. But you can see that the rear axle is overloaded. You see that here from this step to this step. It's not just driving forward. Also the rear is sliding. It starts to slide. So it was already too much what was requested from the rear axle. And now, because of this sliding, the rear of the car is coming on this grass area. And the grass is not flat. So there is, it's pretty wavy. So there could be a form contact between the tire and this wavy surface, where the tire can really be locked to an obstacle. And this happens here, and the consequence is that this car starts to roll over. So this is a typical situation which happened in the past pretty often. If a very, very abrupt steering maneuver was necessary at high speeds, I'm pretty sure that this guy here has also activated the brake. And activating the brake means also to weaken the opportunity to transmit side forces. So it was a very critical situation, and you see the car gets completely unstable. No? Now let's have a look on this situation a little bit more in detail. What can we do to avoid such a situation? What we have seen is that shortly before the car was hitting the grass area with the rear axle, it starts to slide. So it was unstable. So the rear axle was not supporting enough side force, and so it starts to slide. And this behavior of a vehicle is called oversteering. No? It means I steer with the vehicle, I introduce a steering action with the steering wheel, but the response of the car is stronger than expected. If this is the case, then we say the vehicle is oversteering. And this is the situation shown here. The driver intends to follow this line. This is the course which is intended. But the car is oversteering. So it corners stronger than requested by the driver. Now what to do to avoid sliding? This would be sliding. And what is done in a ESP system is to activate the brake at single wheels, plus to control the motor control to reduce driving force. So first what is done, if it is recognized, so there are some sensors who are able to, and electronics which are able to recognize that the vehicle starts to slide. There's a sensor which measures the rotation around the vertical axis, so it can be recognized. If it is recognized, first the traction force is reduced. This has two positive consequences. Less traction force, rear axle drive, reduces the longitudinal use of the adhesion and gives more room for lateral adhesion. This means the oversteer tendency, which is caused by a weak side force support on the rear axle, is reduced. So more side force on the rear will give better control of the car. Also, less driving torque reduces the speed of the vehicle, which means less centrifugal forces. Also this helps. And then the third measure is on the front left, it is braked. So a braking force is applied on the front left, only one wheel on the front left. This causes this force here, this braking force, and this lever arm here from the center of gravity to that point where the force acts. This creates a torque which is turning counterclockwise and brings the car back to the original requested course and avoids that situation here. So that is how the system acts on an oversteering vehicle. By that braking here on the front, it weakens the side force potential on the front, right? And that's good because we have oversteer. We steer too strong. It's good to reduce steering action on the front. So let's reduce ability to transmit side forces by weakening the side force on the front, at least at one wheel. And this will also help to bring it back to the original intended direction. Okay, so that's enough for today. And tomorrow I will present also what is happening with the understeering vehicle, which could also happen. No? So thank you very much for your attention for today.